equation of the lines in 3D space. Okay. At the end of the lecture of last week, Monday, yeah, we started on the equation of lines. Okay. So basically, the point we were illustrating is, okay, we want to come up with an equation to describe the trajectory, which is the line. So, idea came out is, let's assume this point P is moving along this trajectory. So consider it as a sort of a moving point. Then the trajectory P, whose coordinates are x of t, y of t, z of t, essentially they are going, each one of the coordinates, they are going to be a time function, right? So what we want is, we want to come up with a function describing this x of t, y of t, and z of t. All right. So basically, the idea here, we said we want to come up with a so-called parametric equation. Okay. So parametric equation. This is the kind of a new concept. Okay. We will talk about the details of this parametric equation in general, and not just the lines in 3D space. Is a mic on? No?
It's just quiet.
Is it louder? No? What's going on here? Let's try this one here. How about this? How about this one? No? A little better? Okay. Let's bump it up a little more. Okay, that's the highest I can go from there. Is that better? Yeah? Okay. So let's look at how we derive this line equation right here, okay? Yeah. I'll give you two different methods that are here, and the first one is sort of making use of physics, kind of easier to understand. The second one will be making use of that vector property here. Okay. So the first method is this. Let me give you a couple actual points here. Let's assume the Q naught points, okay, is -1, 2, 2, and the Q1 point is 1, 3, -1. Okay. So we have two actual coordinates for Q naught and Q1, and assuming that the P is going to be moving along the line, okay, described by Q naught and Q1. Okay, so now we're talking about moving, so let's assume we have a constant speed here. Okay, so constant speed. Okay, so for example, I'll do this one here. At t equal to 0, we're at this Q naught. And at the t equal to some other time, capital T, we're at Q1. Okay, so that Q naught is here and Q1 is here. So at the t equal to 0, at the t equal to capital T at here. Okay, and at t equal to t, of course, at any other t time, we're at that point P. Okay, so you give a different t at a point P. Okay? So because we're assuming constant speed, as you know that basically what does speed mean? Speed is a displacement divided by time, give you the speed, right? Yeah. So essentially from Q naught to Q naught to P, okay, that's a displacement. Okay, that's displacement. Divided by from Q naught to P, how much time did it take? We said it takes this small time t here, right? It takes this much time to reach that. Okay? And from Q naught to Q1, how much time did it take? This capital T here. Because a constant speed, so this divided by small t, this one divided by capital T, they should be the same thing, same speed. Okay? Yeah. So that's the condition based on assumption here. Okay? So Now let's plug in the known quantities and also the unknowns here. So the point P, if you see that point P, these are coordinates here, right? Yeah. So what do we have? Q naught P, that vector, essentially is what? It's x of t subtract, which one? Subtract this -1 here, and which becomes what? +1. And y of t subtract the 2, and z of t subtract the 2. Okay? Yeah. Is that good? Yeah. Okay. So I am going to multiply the small t to the other side here. Okay? Multiply to the small t to the other side. Q naught Q1. Use the coordinates of Q1. Subtract the coordinates of Q naught. So what do we get? 1 minus that. 2. 3 minus 2. 1. -1 minus 2. Okay, is this, right? Yeah. And then divided by capital T times a small t. Okay, times small t. Is that clear? Yeah. So now let's store these things out. If you time the small t into the bracket, into this vector, so basically this is 2t, this is t, this is -3t, right? You have two vectors on both sides equal sign, equal to each other. So which means the component of here should equal to the component at here, right? So very simply, we got x of t plus 1 equal how much? Equal to 2 over capital T times small t. Okay? And y of t minus 2 equal to 1 over capital T times the small t. And last one is z of t minus 2 equal -3 over t times t. Was that good? Yeah. So sort it out one more step at here. So we got x of t equal to -1, move the 1 to the other side, plus 2 over t small t. Y of t equal to 2 plus 1 over t small t. And 2 plus, no plus, minus 3 over t small t. Okay? Yeah. So now you see what we end up with? We end up with 3 equations. Exactly what we're looking for, right? We want to come up with an expression for each one of the coordinates. You look at the expression here. This capital T is known. Okay, so well, we can plug in certain numbers, try it out. And this small t is a variable. So that's the 3 functions for each one of these coordinates. Okay? Yeah. So basically, if you plug in a value of a small t at here, what do we get? We get a set of coordinates here, right? A point. And that point is guaranteed to be on the line described by, connected by Q0 and Q1. Okay? Was that good? So this is basically a line equation, okay, in 3D. Okay, it's a line equation in 3D. So we're using the kind of physics that are here to derive this line equation. So if you try it out, let's say we plug in a different value of a t at here. So for example, if we give a t equal to 1, and we give a t equal to 1, and then we can try another value here, okay? So for t equal to 1, what do we end up with? We end up with x of t equal -1 plus 2t. And y of t equal 2 plus t. And z of t equal 2 minus 3t. Okay? Right, that's what we end up with this here. Now if I try another one at the t equal to, let's say 0.5, okay? Try at 0.5 here. So I will have another set of equation now. So this is -1 plus what? Plus 4t. And y of t equal to 2 plus 2t. And z of t equal to 2 minus 6t. Okay, yeah. So what does that mean? That means basically, according to what we're saying, when your t is different, basically means what? The speed of the traveling speed of the point P is different, right? It's different. So which one has higher speed? This one, shorter t has shorter capital T has smaller capital T has a higher speed here, right? Yeah. But it does tell us one information though. Okay, it does tell one information, which is, you see, are these two describe the same line? Are they describing the same line here? Yes. So if you try any other different t, you get a different line equation, but they're a different equation, right? So, or we'll call it a different parametric equation. So basically, the point here is, line equation is not unique. Okay, it's not unique. You can have, as a matter of fact, you can have infinite number of solutions for the same line here. Okay, that's the point. So line equation not unique. Okay. And the other point is, okay, the way we derive it is we give this t, we call it time, right? We call it time here. However, if I back off a little bit, I just back off to the pure mathematic expression point of view. Okay, just forget about any physics or engineering. You just look at these two here. What are they? They are just an expression here, right? So the t doesn't necessarily means it's a time. It's just a parameter. Okay, from math point of view, it's only a parameter. Okay, so t is only a parameter, but we can give it, okay, certain meanings here. As I'm going to show an example, we can give it a meaning. It's a time if we need it. Okay, so that's the point. So if t is just a parameter, so that means, do I need to use a t? No. Okay, you can use any other variables you want in here to describe a line. You can use a u, you can use a v, you can use a s, you can use a k, right? So that's basically, you can use anything that are here to replace the t, but of course this is going to be not be t here, right? It will be the corresponding variables you use that here. All right? Yeah. Okay, so that's the first type of method, and I'll just quickly see the second one here. Second method is actually more straightforward. Okay. Any questions from here? Okay. So I'll still use the same idea to here. So let's say I have the Q naught, which is x naught, y naught, z naught. Okay, so this is a known point. So we know this Q naught point here. We have an arbitrary point P on the line. Okay. So now this time I'm not talking about any speed things. So we're saying is, suppose I know another vector v. Okay, I know another vector v, and this vector v is parallel to the line. Okay, we're looking at. So this is a vector v, and it's parallel to the line. Okay, to the line L. In other words, what you're giving is, you're giving a point and a parallel vector to the line. And what will be the line equation? Okay? Yeah. So here's a very straightforward solution in here. Let's construct a vector based on Q naught and a P. Okay, construct a vector based on Q naught and a P. And that can be very easily constructed because this guy, right, equal to the coordinates minus this one, okay? Because Q naught P is parallel to V, well, because V is parallel to L, so for sure this V will be parallel to Q naught P, right? Which means they all pointing to the same direction. However, what will be the difference between these two vectors? The lengths. If the length is the only difference, then mathematically the difference between the two vectors is what? It's just a scale, right? We don't know what the scale is because that P is a moving point. So it could be 1, it could be 2. So we use a variable K at here, or you can use any of the variables to representing the scale. So then we can construct our parametric equation for the line now. So what's this side here? This side is x minus x naught, y minus y naught, and z minus z naught equal k times v1, v2, v3, like this. Okay? Yeah. Similarly, because the two vectors same thing, so you let this component equal to this, the other side component. So what does that give us? It gives us x equal to x naught plus kv1, y equal to y naught plus kv2, and z equal to z naught plus kv3. There. Now this is a line equation here, right? This is a line equation. Okay? It's still a parametric equation, and this time the parameter is k, right? Parameter is k. Okay. So what will be the k value? That depends. So it could be negative infinite to positive infinite. Okay. So anywhere between that. Okay. Yeah. So let's take a second look at this line equation at here, okay? And to gain a little more intuitive informations. Now, if you look at this set of line equations here, and let's look at this portion, and let's look at this portion, okay? Yeah. So first of all, what does this portion here represent? X naught, y naught, z naught. Where is that from? Q naught. And where this is from? V. So basically, as you can see, remember the summary from the plane, and I said if you need to construct a plane, what information do you need? You need a point on the plane and a vector vector normal to the plane, right? Yeah. So same information now, very similar to the line, just like two sides of coin here. So if I want construct line, okay, to construct line equation, what information do I need? I need two information. Number one, I need a point on the line. Number two, I need what? I need a vector parallel to the line. Okay? Yeah. Or the other way around. If you already have a line equation, so I'm telling the question, here is the line equation L. So what do you do first? You can write down two pieces of information immediately before you're doing anything else, which is these two pieces of information, right? So if I write, so given a line equation, okay? Given a line equation, write down these two informations. Okay, So this is very important, okay? Very important. So no matter what you do, before you go ahead and solve any questions, you can always write these two things down based on the given information. Okay? Is that good? Okay. So to if you do not like writing three equations, then we have a slightly better way to represent this line equation. So what we can do is we can alternatively, okay, we can do this. This is x naught, y naught, z naught. So I can define, okay, I'm going to define a vector, okay, not define a point, okay, I don't define a point, I define a vector. And this vector is x naught, y naught, z naught, okay? And I'm going to define the v as euro, v1, v2, v3. Okay. And the x, y, z, that's the point on the line. So this time, we don't use the point P, we use a vector, okay? We call that x of, in this case, it's k, so x of k, y of k, and z of k. Okay? So if I define these three things that are here, then these three equations, okay, these three equations can be shortened into one expression, which is r. So that's a function of k in this case, equal to what? R naught plus t times v. Oh, not t, sorry, k. Was that clear? Yeah.
I'm not sure what variables are what's a v and what's an r.
V is vector parallel to the line, so that's a known quantity.
Okay.
R naught is a vector. So this is basically exactly at the first lecture I was reviewing here. Here is the point P. X naught, y naught, z naught. Okay? So if I write this, x naught, y naught, z naught, what does that represent? Vector. What do you do? Okay? This is the R naught. Okay? This is R naught. Was that good? So let me show you this, how it works here, okay?
What's v naught?
V naught. There's no V naught. V, you mean?
Oh, you said r naught.
Yes, you said V naught, R naught. I think that's where the confusion came.
Okay, one question each time. You have hard time what?
Just tell me the difference between r's and v's.
What's R and V's, right? Okay, let me draw.
From here.
Sure, let me draw this maybe in a better way here, okay? Yeah. Okay, this is the line we're looking at. This is, let's see, actually I call it Q naught, right?
You mean the way you physically wrote your R's and V's?
Yeah, just a second. Okay. This is a Q naught. Is that okay?
Yeah. It's just your r looks like a v.
Oh, I see. That's the. No, it doesn't. V has bigger. This is anyway. Let me rewrite it here. Okay. So this is a P out of here. Was that okay? Okay. So this is what happens here. I'm going to construct vector now. Okay. I'm going to construct first vector is this. Was that right? So that's the vector what? What do I call it? Not, exactly. Second vector I'm constructing is what? Oops. That drawing is from O to P. Okay? From O to P. What do we call that in our case? R. It's not V. Okay? And then from, if you look at the expression here, R, look at this R here, right? Look at this R. Technically, if I draw Q naught to P, draw another one, it's actually a triangle, okay? It's actually a triangle here. So this is a Q naught, this is a P, this is O. This is R naught, this is R. Was that right? So from your linear algebra, what does R equal to? R equal to R naught plus what? Q naught P, right? So what is Q naught P again? Did you see where that from? Was that right? Yeah. Okay. So R equal to R naught plus Q naught P. Okay? And Q naught P is KV. Okay? If you don't like a K, you can use a T or S, doesn't matter. Okay? Yeah. Any other confusions that are here?
I have a question.
Yeah?
So the vector Q naught P is along the line. The vector R is not. That's correct?
Vector Q naught P is always on, well, P is always on the line you're looking for, right?
So vector R is not parallel to the line.
No. Vector R is just the vector representing the point P.
Okay.
Was that good? So this is the first lecture mentioned. There's when you give in a point P in the space, there's a coordinates associated with the point P, and there's a vector representing the vector P position, right? Yeah, we call it position what? Vector. Okay? Yeah. Okay, good. So now, are you ready for some exercise here? Okay. It's actually quite important to understand all the physical meanings behind a given line equation right here, okay? Yeah, so that's very important. So let's look at the first example. I'm giving you a line, okay? This line is 1 plus t, 3 minus t, 2t, okay? And we're also giving a point S with coordinate 1, 1, 5. What we want to find the perpendicular distance from this point S to the line, to this line L. Okay? So this is the line L, and this is S. We want to find the perpendicular distance to the line L. Okay? Yeah. So in the previous lecture, we had an example which is giving a plane and a point. And what will be the shorter distance from the S to the plane, right? So this is the same idea. What will be the shorter distance from S to the L here? Okay? Yeah. And there are actually different ways of solving this. Okay? Each method has its merit. So let's say we're trying a few of this here, okay, just trying to illustrate. Basically, it's always about vector operations, okay? So let's try the first method first. Okay, so you're looking for a shortest distance, just maybe give you 1 minute here just to gather your thoughts here. What direction do you think you wanted to go to tackle this? Okay, just think about it. Just based on what we have done in the past 2 lectures, okay? Particularly the first one, the cross product, dot product, that kind of things. Yeah. And of course, before you move on here, as I said, if you're given the line equation now, you should write down 2 informations immediately, right? What are the 2 information? First, that's right. So let's say we have a point on the line. In this case, what would be the point on the line? So let's call that maybe a P point. Okay, so that point P is on the line. And given the line equation here, what's the coordinate? It's basically what information do we take? We take this information right here as the coordinates, right? Yeah. So which is, in this case, 1, 3, 0. Okay? So hypothetically, let's just say this is a point P right here. Alright? Second information, we have the V vector parallel to the line, which is basically what? The coefficients of these parameters, right? Coefficient of parameters. Okay? So in this case, 1, -1, yeah, don't forget a negative, and 2. Okay? Yeah. So, if somebody insists the V is actually 2, -2, 4, should I argue about that? No. Because why? Because this is only a difference of scale, right? Yeah. Okay? Yeah. Okay? Again, I'm taking a point 1, 3, 2, 1, 3, 0 out of this line here. Now if somebody else do this, he's going to substitute the t with a certain value. Let's say substitute equal to 1 into here, here, here. And he get another set of points on the line, which is what? 2, 2, 2, right? That's okay, right? That's okay because there are infinite number of points on the line though, right? Okay? That actually does open sometimes a door for you, you probably need another point on the line. Okay, just bear that in mind. Is that good? Yeah. Okay, so now you have this information now, right? You have the information. So we're ready to solve this question. Okay? Yeah. So what direction just think about it, you wanted to go from here. Okay? Distance. So you wanted to obtain this distance, d at here. Okay? Yeah. So think out loud, in any directions that you can go, and even just think of it in terms of geometry, anything. Vector PS, good. That's a good point here. So you construct the vector PS, right? So what would you do from here?
That's what we're working on.
Yeah. Excellent. So you want to project the PS to where? Sorry. Onto the T? D. I see. Good. So that's an excellent point because in when we learn dot product, there's one thing I emphasize is if you want to know the length of a certain projection, what do? You use the vector dot the what? The unit vector of that representing that direction. Was that right?
Yeah.
So I like that. So if I want to find a D, I need what? I need to find the unit vector representing that direction. And then I can just use the PS dot the n hat to find the distance or the length. the projection, right? Yeah. So, but that does bring a question. How do I find the n hat though? Yeah.
Okay, this may not be the most efficient method, but I think it will work. If you take PS and V and do the cross product, and then take the resulting vector and V, you get a plane, and then that n is the normal vector of that plane.
Excellent. Did anybody get that answer here? So what he's saying here, so what's your name?
Finn.
Sorry?
Finn.
Finn. So when Finn's, what Finn's saying is, he's not going to do the dot product with the n hat, right? So he's going to project the PS to this V direction first. So he's trying to find this portion first. And once you have this portion, then you get this portion. Is that saying right? That's what you're saying, right?
That wasn't what I was saying, because that was more efficient than what I was saying.
Oh, is that right? Okay, so that's a shortened version of his answer. So, that's definitely doable here, right? It's definitely doable. As a matter of fact, when we do the dot product, we said we did a projection. We said, projecting this to one direction. And what about the other one? So we use this vector subtraction to find the other one there, right? So that's basically doable here. So let's try this first, okay? Let's try this. Maybe you can explain that again. We can try yours after this. Okay, so let's see. I'm gonna call this portion here. This is a projection, right? We're doing projection here. So one projection is this. So basically, you have two components of the projection of this PS vector. One is this direction, and one that direction. So let's say maybe I call this as a PS parallel, and this is a PS perpendicular, right? That's what we did in the first lecture. Okay? And PS parallel, it's a vector. So it's a vector meaning the vector has two components. One is length, the other is direction, right? Yeah. So for the direction, it's defined by the V. So the V, we don't need the V, we need the what? V hat. For the length, as we said, we use dot product. So we need this PS dot V hat. Okay, right? That's the meaning here. So length and direction. Okay? Yeah. Okay. So now let's try this out here. Let's see. We're going to do the calculation now. What would be the V hat then? You have the V here now. Remember, how do we calculate V hat? What do you do with the V? Exactly. Normalized by its magnitude. Okay? Yeah. So that's easy. So 1, 8, 1, 2. So normalize that. The magnitude is 1 plus 1 plus 4, so 6 root 6. Okay? Root 6. 1, negative 1, 2. And PS, okay? PS is the, use the coordinate of S, subtract the coordinate of P. So we have S over here, we have a P over here. So 1 substitute 1, 1, negative 2, 5, 5. So 0, negative 2, 5. Okay? That's PS. Okay? Yeah. So now the rest of this is pretty simple. Just substitute into this formula here. You do the rest of the calculation. So a scalar value times unit vector V. So quick exercise, you'll find out that this is actually equal to 2, negative 2, 4. Okay? Yeah. So that's the projected vector in the direction of V hat, or in the direction of a line. Okay. So the next step, calculate PS perpendicular. Okay. PS perpendicular equal to what? Yeah. So PS vector subtract the PS parallel. Okay? Yeah. So substitute everything into it. You got the two vectors, just subtract each other. We have, okay, negative 2, 0, 1. Okay? So try this calculation yourself, okay? If you need to go over this exercise again, try the calculations. In the end, so what's the d then? D equal to, what is d equal to? The distance. The distance is, well, the length, right? The length of what? PS perpendicular. Okay? So absolute value PS perpendicular. And that's what? Root 5. Okay? Yeah. Is that okay? Yeah? Okay, so I think it's worthwhile. Let's do another method here, okay? Okay, so the first method used dot product. How about cross product? Can we use cross product? Okay, can we use cross product? Before thinking of a cross product here, just give you a hint here. Let's just say this is theta, right? Let's just say this is theta here. If you know theta, how do you get to d? If you know theta, how do you get a d then? As somebody said, d equal to ps times what? Sine theta. Okay? Yeah. So the question is, where can we get that theta? Right? A sine theta. Okay? Dot product, yeah. But yeah, dot product, you're thinking dot product is a cosine theta, right? Then you get a theta and you get sine theta. Right? Yeah. So, but if you remember, what's the formula for cross product? When you use PS, let's just say in this case I'm going to cross that parallel vector V. Okay? The magnitude of the cross product, if you remember, what's the formula? It's what? PS times what? Times V times sine theta. Because you look at the line at here, when we say this is the angle between PS, the line, it's the same thing as this is the angle between PS and the vector V here, right? Vector V. So now you see, if I rearrange this slightly, what do we get? Is that okay, right? And what is this? That's basically the D you're looking for, right? The D you're looking for. So in other words, the D equal to equal to this, right? So if you look at the right side here, can we calculate the numerator and denominator? I mean, the denominator is pretty easy. That's basically the absolute value or the norm of this vector V, right? And this one here is basically what? That's a cross product. Do you know how to cross product? Do you know how to do a cross product of given two vectors? Yes, of course, right? And do you know how to do the results? Yes, you do. So basically, this is doable now, right? Yeah. So you probably need to do this first, okay? If you remember that, that's essentially the determinant, okay, of this matrix over here. Okay, yeah. And once you get this, okay, use your calculation skills. Okay, you'll be able to, okay, try it out here. Okay, yeah. So I'll write it down right here. So I5 2. Okay, yeah. So seriously, you need to exercise those calculations. Okay. Then calculate the norm divided by the V, you'll see that it's exactly the same results as in method number 1. Okay? Yeah. So let's try the third one here. Okay. Any questions? Okay, yeah. So the third one, okay, let's go back to the original thoughts here. As one of the students suggested, if we have the n hat, we can use just a ps dot n hat, right? Dot n hat. So is there any way we can find this n hat then? Right? So that's basically the sort of thinking for my third methods. Okay? Yeah. So I'll give you a little bit of time here to think about how do we find that n hat? Right? Through what kind of relationship can we find that n hat? And you can think of what would be the relationship between this n hat and the given conditions at here. Yeah.
Can you say that the dot product of that n hat with the line is going to be 0 in the perpendicular?
Exactly. That's excellent. That's one of the very obvious conditions. You see, n hat is perpendicular to v, so which means the dot product of these two vectors are 0, right? So let's try this. Okay, I'm gonna know what n hat is, so I'm gonna let n hat, okay, equal to something over here. Okay. However, okay, maybe what I should focus on is not n hat. I'm going to focus on any vectors in that direction. I'll call it n here. Okay. Yeah. Sometimes finding a unit vector it's not that easy, but if we can find n, we can just normalize it to get n hat. Okay. Yeah. So let's let n equal to a certain vector. Okay, n is certain vector. And as sorry, what's your name?
Carl.
As Carl suggested, Carl suggested n is perpendicular to v. Okay, so which means n dot v is 0. Okay, n dot v is 0. N dot v is 0, let's try it out. We know v what it is, right? So v is 1, negative 1, 2. So I'll just plug in the conditions out of here. Dot 1, negative 1, 2 equal 0. Okay, equal to 0. So what we end up with? We end up with actually what? Carry out n1 minus n2 plus. Okay. Does that make sense? Yeah. How many variables? 3. How many equations? 1. So how many solutions? 0? Infinite, right? You have one equation, 3 variables, you have infinite number of solutions. What does that mean? So this is the line here, and this is the vector parallel to the line. And you're trying to find, just only based on this condition, okay, the dot product equal to 0. So you're trying to find a vector perpendicular to this line, so which means what? That vector could be this way, this way, this way, this way, this way.
So that's a plane.
Nope. This is the line here, right?
Yep.
The line could be, the vector n could be pointing this way. Could be this way, this way. So pointing 360 degrees anyways, but always point perpendicular as long as it's perpendicular to the line you're looking for. Does that make sense?
Yeah.
So just this condition, that's what it means said here, right? So you have this line here, you can have this n here, and you can have the n pointing up. Basically 360 degrees, but as long as it's perpendicular to the line. Okay? Yeah. So that basically brings us to question here. That can't work, right? But we actually only need one, yes.
Can you put the coordinates for S into it?
Yes, we have to. Right? The point is, how? Does that make sense, right? So we don't need any direction. We actually only need one direction. Does that make sense? Yeah. Or in other words, if you look at this case here, geometrically describe it, that n needs to be where? The vector n needs to be in the same, with the line L and what else? PS. So basically, that n needs to be in the same plane determined by the L and PS. If that constraint is applied, then that's the n we're looking for. That make sense? Yeah? So now the question is, the second question, if that's the wording, okay, I want an n which is in the same plane, or not necessarily same plane, which is basically parallel to the plane determined by L and PS. Was that right? Yeah. So let me write down the statement here, okay? And n is parallel or same plane, okay, determined by V and PS. Okay? Yeah, needs to be this. The first condition, dot product equals 0, constrained the n to be perpendicular to the V. And this condition will constrain it to be the direction we're looking for. Okay? Yeah. So, if this is the language see here, so mathematically, how do we apply this constraint basically? I'll draw something out here, okay? So this is a PS, and this is a V. Okay, this is the plane. And the n needs to be within this plane and here, okay? Just for this statement. Or parallel, doesn't matter, okay? Yeah. Okay, so what does that mean? If n is in this plane, so you know when you do things, you can always do, just forget about n first. If you have PS, you have V here, we can always do what? Cross product to get exactly to get another vector perpendicular to the plane. So let's call that I'm running out of the notation. R again. So okay. So sure. Yeah. Okay. What's the relationship between R and V? Oh, sorry. What's the relationship between R and N? Dot product 0. Yeah, you should just say perpendicular, right? So basically, they are perpendicular. That means dot product 0. So that exactly the language, the math expression to translate that plain language here.
Are n are parallel?
Parallel?
Yeah, are they parallel?
No. See, this n is within the plane or parallel to the plane, right? So vector is a free vector. You can put a vector here, you can move around as long as you don't change the direction. That's the same vector. Why? Because the same direction, same length. Okay? Yeah. So when you hear it's within a plane, when it's here, I'll see it's parallel to the plane, right? Yeah. Okay? So that means n dot what? PS cross V equal to 0. Okay? So PS cross V, we actually found out already in the second method. Then you do the dot product. So that means we actually end up with another equation here, right? Another equation. So I will just write it down here. So we end up with n1 plus 5n2 plus 2n3 equal to 0. Okay? Yeah. So we have one equation at here and one equation at here. Okay? So 2 equations, how many unknowns? 3. Again, how many solutions? Infinite. Only they're still infinite. But what does this infinite solution mean now? Is this infinite the same kind of meaning as the other infinite? No. The other infinite, you have pointed all different directions around it, right? But this infinite is actually, it's going to point to the same direction, but different lengths. But that doesn't matter. We don't care about the lengths because we're going to normalize that to get the n hat, right? So basically, these 2 is enough now. So let's do this here. Let's get we only need one solution based on the 2 equations here. So how do we approach that? We can use equation. There's different ways to you can use equation number 1 subtract 2. We get 6n2 equal to 0. So that gives us n2 equal to 0 nicely. Okay. Yeah. And then you sub the n2 equal to 0 back into the equation. Let's say number 1. And we got n1 plus 2n3 equal to 0. Okay? n1 plus 2n3 equal to 0. So at here, what you can do is, you can simply, let's say, I'm going to let n1, whatever you can do, you can let n1 equal to 2, let's say. Okay? But just don't let it equal to 0 though, right? Yeah, you're going to get a 0. Let n1 equal to 2, so that means n3, 2 at here, n3 will be, what would that be? You put a 2 at here, n3 equal to -1. So n2 is 0, n1 is 2, n3 is -1. So we get a solution for n. Okay? Can you come up with another? Yes, you can. Okay, so but they all point to the same direction. Okay? Yeah. So we got n. We normalize this n at here. Once normalized, it's all the same, and that's 1/5 at here, 2, 0, -1. And the last step is to do the dot product. Use the PS dot n hat. Right, PS dot n hat. Okay? Yeah. Now you probably will see that the dot product end up with actually a negative number. So, but you're looking for a distance, so just take absolute value of the end results. Okay? Yeah. So D equal to, you can put an absolute sign right here, equal to that. That's going to be exactly the same kind of solution as number 1 and 2. Right? So I spent a lot of time here trying to, basically this is kind of question you can see different directions, but they're all making use of the dot product, cross product, and the ideas of vector based on the given information of the lines, vectors parallel to it, line points on it, right? Geometry relationship. Okay. Yeah. Think carefully what's going on behind these things here. Any questions set here? Okay. All good? All right. So let's look at another one in here. So this is a little bit more interesting question right here. Suppose I have a cat which is traveling along a straight line. Okay, so this is Tom. It is traveling along this straight line right here. Okay. So this, I don't have a Z, basically means this is the in-plane situation. And this is a mouse. Jerry right here is being chased by the cat. Okay? Yeah. suppose that, okay, the cat and the mouse are all traveling at a constant speed. Okay, constant speed. And for the cat, the speed is, okay, v1. So we're just gonna take the parallel vector out of the line equation. So 2, -3, 0. Okay, that's the cat. Okay, is that okay? Yeah. So that's the speed. Okay. And the mouse, we're gonna just take this one in here. 1, 4, 0. Okay. So the question in here is, will Tom catch Jerry? Okay. Yeah. So before we answer this question here, okay, we actually should think about another question. Okay? Yeah. The question is, will the trajectory of Tom intersect the trajectory of Jerry? Was that right? Yeah. Because if you don't, of course you don't need to do anything, right? Yeah. Now this is an in-plane situation, so it's actually simpler. So basically, hypothetically speaking, if they're in a 3D space, okay, a 3D space, then you have what are the type of relationship between two lines in 3D space? You could have what? Like parallel like this, right? And you could have two lines intersecting. What else could you have? No relationship, meaning the two lines like this, right? We call that skewered, okay? Skewered. So that's a three type of relationship here. But in plane case, for in-plane case, you actually only have what? Two different situations. One is the line parallel, the other is intersect. Okay? Yeah. So now the question is, how do you quickly decide whether the two lines intersect each other or not? Sorry? One by one? Who wants to answer this? Dot product what? Make sure what equal to 0?
By a super solution.
By what? Super solution. Find a solution.
Like linear. Sorry.
Oh, I see. You're trying to solve the two equations here, right? Okay, but what's the easiest way? What's the easiest way to find out the relationship between the two lines? When the two lines are parallel, what does it mean by the...
They have the same normal vector.
No, okay, back off a little bit here. When you're given two lines, what do they say? What's the information you want to write down first? Point and parallel vector, right? So you can have two parallel vectors corresponding to each line. And if you want to know the lines are parallel or not, what do?
Are the lines, or are the two vectors just a scale of each other?
Exactly. Right? You can just look at the two parallel vectors. Are they a scale of each other or not? If they are, that means the two lines are parallel. If they're not, if they're in plane case, okay, then they intersect each other. Okay? Excellent. Yeah. Is that easy enough? Yeah? Yeah. So back to here, what's the parallel vector here? What's the parallel vector here? Are they parallel to each other or are they a scale difference? No, right? Now, back to linear algebra, what does the scale difference between these two means? In linear algebra, you learn there's a concept called the linear independence, right? Yeah. So that's the idea here, okay? So of course they don't parallel. That means the two lines will intersect each other. If two lines intersect each other, then the next question is, will the cat catch the mouse or not? Right? Okay? Yeah. Okay, so if you're going to solve the question in here, so you have to, let me just maybe roughly draw the draw the lines in here to illustrate the idea, okay? So you will have a line like this, and you will have a line like this. Okay? If you draw it actually, the two lines more or less like this. Okay? This is the cat's line. This is a mouse line. Okay? Yeah. So the cat is going to move along here, and the mouse will move around here. Okay? Yeah. So as you will see that when you draw the vectors when you draw the vector v1 and v2 out, they're actually pointing one this direction, one that direction. Okay? Yeah. That's almost to the right scale. And then think about this. Okay? So the cat will travel along here, the mouse will travel along here. The only question is, if you look at the equation in here, what I'm writing in here is all t here, right? Basically, they always exist in the same space. So as time changes, both of this cat and mouse will change at the same time, the position. It makes sense, right? So basically, the t representing the time change for both of these things here. And if the cat can catch the mouse, okay? So that means at a certain time t, the cat and the mouse will arrive at this point exactly at the same time. That's what it means, right? Yeah. If you don't like cat and mouse, you can think of a missile targeting an enemy, right, moving target. Okay? So now let's do this. If the cat and the mouse arrive at exactly the same time at this point, so the question here is, what would the question? So the question is, what does that mean actually?
They have the same point.
They are at the same point, but yeah, what does that mean again? The same points, same time. Yeah, I said that. So you have the coordinates, right? We have the coordinates x of t, y of t. So basically they're all moving. So when they arrive at the same time, at the same point, this is x of t. This is what? X of t. Yeah, go ahead.
Can you set each x and y to each other and solve? If you get the same t they are, if they don't, then it's not bullshit.
Exactly. As Carl suggested, that's exactly my point here, trying to lead you to the point. When they arrive at the same point, same time, we have to have the coordinates of these two the same at the same time, right? At the same time. But we don't know that yet, okay? Right? We're trying to find out, okay? So basically, which means we're going to let this x equal to that x, and we're going to let this y equal to that y. Because y, you see, if I let this x to this x, I can get a solution t. If I get this y, I can get another solution t. But guess what? If they're arriving at the same time, same point, the t has to be what? Equal. Yes. Okay? Yeah, so let's check that out. So we let -4 plus 2t equal to 1 plus t. We're going to let 7 minus 3t equal to -6 plus 4t. Okay? So the first one will give us t equal to, so plug t over there, that's t, 4 over here, 5. Second one, pull the 3t over here, 7t, 6 over there, 13, so that's 13 over 7. Okay? So two t's are different. That means the cat is not going to catch the mouse, right? So no. Okay? No. Okay. Is that logic clear? Yeah? Okay. Now I'm going to ask you a different question now, okay? Yeah. We said they're going to intersect. Then what is the intersection point then? That's irrelevant to the question from the first one, the cat catch the mouse. Completely irrelevant. What's the intersection point between the two lines? Okay, how shall we tackle this question right here. Yeah.
Can you rearrange one and plug it into the other?
Exactly. So, but the whole point here is actually I'm trying to let you figure out, you be careful here, the meaning here, okay? If I'm going to calculate intersection points, so we're going to do something to this equation first, actually, okay? So when we talk about intersection of two lines, forget about the physics. Basically, forget about the physical meaning of the t. It's not a time anymore, okay? It's not a time anymore. We're going to just look at these two as two parametric equations mathematically. So instead of writing t at here, I'm going to write the two equations slightly different. I'm going to use s here. I'm going to use a k at here. All right? Yeah. So I'll just do this. I'm going to let the L1 or L cat is x1 of s equal to -4 plus 2s. And y1s equal to 7 minus 3s. And L2 is x1, I'll use a k, 1 plus k. Y of k, this is x2 equal -6 plus 4k. Okay? You see my purpose at here is I'm writing them actually purposely to be different. This is x1, y1, this is x2, y2. And this is not in terms of t, this is in terms of s, that's in terms of k. Because just trying to re-emphasize the idea. The line equation, a parametric equation. You have an infinite number solution, you not necessarily just have to use a t, you can use any other parameters. Okay? Then, because we want to find the intersection point and we already know they must intersect. So when they intersect, that means the coordinates that are here should be the what? Coordinates of the other side. So the coordinates should be the same. Coordinates should be the same, meaning this should be the same as this, and this should be the same as this. Right? So now let's do this. Okay? Yeah. So we construct two equations based on the condition. We want them to meet or to intersect each other. Okay? So two equations and two unknowns. So you can solve for s and k. Okay? You can solve for this. And once you get s and a k, if you sub the s and a k back into the line equation, you will see that that's going to be the intersection points. Okay? Yeah. Was that good?
S is just 3.
Sorry? Oh, what if there's 3?
No, S only needed 1.
Oh, 33. Sorry. Didn't. Oh, that's just 3, I see. Yeah, of course. Yeah. Okay. Last question. Let's get back to the cat and mouse. Okay? Because in the previous one, the cat couldn't catch the mouse. So let's say now you're the judge here. You want the cat to catch the mouse. What can we do to the cat such that the cat can catch the mouse? Okay? So let's just see. This is the speed of the cat. Okay, this is the speed of the cat. The cat is not going to change the trajectory. The cat is still going to go along the same trajectory. How can we modify the cat's speed? Or this initial point set here, such that cat can catch them. So let's tackle each one here. So let's leave the other one. So the first one, let me do this. How can we change the speed at here, such that the cat can catch the mouse? In other words, what will be a new speed for the cat? Okay? Yes.
So could you use a proportionality of the two p's and use that as a scalar for the v?
Exactly, proportionality. Why proportionality? Because the cat is not moving anywhere, it's still constant speed, still on the same plane, on the same line. So if it's on the same line, the speed of the cat, the new speed is simply just going to be a proportion of this guy here, right? This guy. Okay? Yeah. So instead of saying a scale of this, I think it would probably more making sense to say a portion of what? A scale of, instead of saying scale of this, I probably say more of a scale of univector, right? Univector of that direction. Okay? So let's just see. Okay, what could be the new speed for the cat? A couple of minutes, okay? So I'm going to call this is a V1 is the cat new speed.
What is new speed of the cat?
Yeah. The V1 new. And as a proportion, we said this is going to be a proportion or a scale. It's going to be a scale of V1 hat. Okay? Okay, 1 hat. Same idea. Okay? Yeah. So V1 hat is V1 over V. 1. Okay, the magnitude. So we have the V1 and we can calculate okay, we can calculate this. Then the whole point here is now, what would be a possible value of a C such the cat can catch the mouse now? Okay? If this is the V1 new, then as a matter of fact, the line equation for the cat can be rewritten, right? Can be rewritten. So line 1 or the line cat, if I want to rewrite that, it would be what? The same initial point, but it's going to be the line based on this new parallel vector. Okay, new parallel vector. And that's going to be C 2C over root 13 times t. And y is 7, same as before, 3c over root 13 times t. Okay? Yeah. So this is a new line equation. Well, not a new line equation, but actually the same line, right? But it's just different equation now, different parametric equation. Same idea now. You want the cat to catch the mouse, so what do? We have to let this x the same as the other x, the y the same as the other y, right? Now, but remember, okay, remember this. Just a second here, let me just see, did I make a mistake? Yeah. Now remember, this portion here, when we are solving the intersection point of two lines here, we have this k equal to 1, right? We have this k equal to 1 for the mouse line, okay, for the mouse line. If I change this k back to the t, okay, back to the time t, what will be the physical meaning for the t equal to 1? Yeah, 1 second. That means what? That means the mouse, at the t equal to 1, the mouse reach where? The cross point. Does that make sense? So basically, at t equal to 1, the mouse reach intersection point. Okay? Intersection point. Okay? We have the intersection point. To sum the k into the equation, we have the intersection point. The intersection point, I guess, intersection point is, if you put it as a 2, negative 2, okay? Intersection point. Okay? And if you want your mouse to catch the cat, if you want the cat to catch the mouse, That means the cat has to reach the intersection point also at t equal to 1. Exactly. Right? And also at where? At x equal to 2 and y equal to -2. So now can you solve for this C now, right? Okay? Okay, so you're dismissed. Any question?